All right, so we talked about a bunch of attacks, and we talked about poisoning attacks where you modify images or input data to cause a model to learn bad habits, and evasion attacks where you modify an image or whatever other input so it's misunderstood by the model. And this is the only defense I've seen that I could actually go through hands-on. And it was, what's interesting, there was a research paper demonstrating this, and I got it working, but the research paper did not demonstrate that it worked in any way that I could understand. It had graphs full of strange, complicated parameters. So it took me like a week to get this project. I think I spent a whole week writing this project because I found a way to show simply that it works. So what we're going to do, this is called deep neural rejection. And the idea is quite simple. If you remember the evasion attacks we did before, you would have a number, but we're trying to classify numbers, and it would add some extra snow, like dots around the edges. So a human could look at that and say, that image has been modified. It's got snow on it, and the other ones don't have snow on it. So that's all this does. You take the working large language model, and then you add on the side another neural net, which abstracts just a number from it. And in a simple case, it would be something like the average brightness, but this is going to learn to make some other measure of some parameter of the model, and it's just going to detect, after classifying, measuring 3 different properties of it and combining them, it's going to have a number, and it's just going to find the outliers. These are the ones that look funny, the ones that are not in the average area for this measure of the geometrical properties of the image, so you just throw away the ones that look funny. It's pretty simple, just what a human would do. That one looks weird. It's got those funny dots on it that shouldn't be there, and this turns out to be quite effective. So I already started the first bit importing and training. This downloads a pre-trained model, so we don't have to train it. And there we are. So it's created a model, and we have should show. Oh yeah, training set shape. It's 1,000 images, each with 784 pixels, and of course 1,000 labels. So that's the data we're using for the test set. So we'll take a look at the images as usual to see what they look like, because this, I think, is the most powerful part of these projects, is making sure you can see what it's doing. All right, and so there's the images, and they're just more of the same images we've seen before, handwritten numbers that are often sort of poorly formed, and the right label there. All right, so we're going to see the predictions of the unprotected model. The deep neural network model here. All right, and here as before, we see various predictions. So the first 3 numbers show the image number, the predicted classification, and the right answer. So you can see these are ones, looks like it got most of these right. Here's one that got wrong. It predicted a 5, but it was really a 3. All right. So then this one, it predicted a 6, but it was really a 5. So there's a few it gets wrong. All right. So now we're going to attack the model using an attack we've used before, the C-attack evasion PGD-EXP. That's one that will carefully calculate what modifications to these images will most confuse the model. And it has access to the whole model, knowing all the parameters and everything, so it can calculate the most efficient evasion attack. It should show us, yep, it's going to show us the digits here. You see in 5 to a row, so it's going to do the first 5, the next 5, the next 5, and the next 5. So they'll be nice and big, easy to see. Of course, it takes a bit of calculation to do this. Shouldn't take too long, however. Well, while it's running, let's look at the answer here. So you see this, like you said before, these are the evasion images. So it takes the original number and it adds just a little bit of snow, a little bit of extra pixels around it, which is what confuses the model. All right. And now down here, we're going to see the results, the number correct predicted. And so you can see all these evasion attacks worked. All these are wrong. Number of successful evasions, 20. So all these 20 generated images fooled the model. So the model is very vulnerable to this evasion attack. And now we're going to train deep neural rejection to give it a defense against that. So this is what adds the deep neural rejection model to it and trains it. And then it's going to set the reject record threshold so it rejects 10% of the samples in the test set. And here's the result. You'll see some of them have an R here, which it's going to, and that means here's what it predicted. It predicted 7, but the right answer was 7. It predicted 9, but the right answer was 9. And here, it refused to predict anything. This is a model it rejected. It rejected this and was not willing to make a prediction, so it didn't get it wrong, and the same here. So the point of this is it will notice when a model has been, an image has been modified so I cannot correctly predict it and refuse to predict it. The sort of thing that most AIs do not do. Like I talked about ChatGPT and text generators will not tell you when they don't know the answer. They will just make up a lie. And here's how we're preventing that, by having another layer that will detect if things look funny and not bother and tell you I cannot produce an answer when it can tell that something's wrong with that image. And so you can prepare attack images for the complete DNR model. I think I won't bother doing it live because it's being kind of slow. So even though you have, and even if the attacker has full knowledge of the whole model and full knowledge of the DNR, and you do the evasion, it still blocks most of the evasions. You see here, here's testing 20 evasive images. These are the same kind of evasive images with extra snow on them. And you see now only 6 out of 20 are successful. The rest are correctly rejected, giving you a -1. So the DNR model lowers the effect of the poisoning. The unprotected model, you can fool it 20 out of 20 times. The protected model, you can only fool it 6 times out of 20. So that's an easy way to see that the defense actually works. And this is, I think, quite consistent with the reports I've heard that the more modern things like Microsoft 365 Copilot is less likely to hallucinate. And the research papers I've seen said that we can cut the hallucinations down by like 50% by adding another layer of neural network that looks at the answer to see if it looks suspicious. So it makes sense. These defenses are not perfect, but they are effective, and presumably as time goes on, we will have better and better defenses. So that's what I wanted to show you. Let me stop this recording.